What I'd like to discuss with you over the next 30 or 40 minutes is a work in progress. This is a draft briefing from a study which has been conducted over the last 3 years by the International Academy of Astronautics. It's the first international assessment on the topic of space solar power. As you know, there have been a number of national studies, in-house work, private work. This is the first time that there's been an international examination of this topic. Next, please. So the study was formulated in 2007, was kicked off in 2008. The goals of the study were to determine what role solar power from space might play in meeting the need for abundant and affordable and sustainable energy over the coming decades, to assess the technological readiness and the risks of key technology options for space solar power, and to frame, if it was appropriate, a notional roadmap for the international community as a reference point for going forward with space solar power. In addition, the study looked at the potential opportunities and evaluated those for the use of space solar power technology and systems for space missions, as well as for space solar power in terrestrial markets. And it looked at opportunities, at least in a very cursory way, for the introduction of extraterrestrial materials into a space solar power industry. Next, please. This was the overall global environmental and energy context for the study. This is not a position of the Academy. This is simply taken from the literature, and I'll come back at the end and tell you what the status is for the publication of the report and when it'll be available and so on. Essentially, there are several competing forecasts for global population. The high takes us by the end of the century to something like 12.5 billion people on the planet. The low says that it'll be down at around 5.5 billion people, substantially lower than it is today. Today it's at approximately 7. And then something in between. But there is a generic consensus that barring, which has actually now been ignored by the Intergovernmental Panel on Climate Change in a report that's coming out momentarily. There was a press release just a few days ago. But the fact of the matter is that there is a consensus that over the coming century, if economic growth continues at a reasonable level in India, in China, in sub-Saharan Africa, and in Southeast Asia, in the Pacific Islands, Pacific nations, that the annual energy consumption globally, and this is all forms of energy, will grow from where it is today at approximately 120,000 billion kilowatt hours per year, and this is all types of energy, to 4 times that, 480,000 billion kilowatt hours per year by the end of the century. And this basically reflects the fact that most people who don't currently have abundant and affordable energy want it. And they will, and are taking steps to get it. This is the only way economies can grow. It's the only way that people can escape poverty. It's the only way, etc. However, in order to achieve greenhouse gas emission limits, which have been projected as essential by the Intergovernmental Panel on Climate Change, something has to be done about the mix of energy sources, and this was spoken of at some length by Daryl earlier and by others. And essentially, there is a cloud of almost 200 different scenarios being looked at by the Intergovernmental Panel on Climate Change. The Academy took a somewhat different approach, which I'll talk about in just a moment. But if you just look at the two extremes, one extreme says that we never do much better than we are now, and that while energy consumption is growing by a factor of 4 over the next 90 years, the percentage share from renewable energy sources stays about the same, i.e. the amount of renewable energy also grows by a factor of 4. That won't do anything about climate change. There's the high case, or rather the best case, which says that if you really want to drive down greenhouse gas emissions and to limit the growth in greenhouse gas concentrations in the atmosphere to a small multiple of pre-industrial levels, that by the end of the century, 90% of 480,000 billion kilowatt hours per year has to come from renewable sources. And so this basically means that something like, well, if you multiply this number by 4 and you look at it's got to grow to 90%, it's a stupendous increase in the amount of renewable energy that has to somehow be achieved over the next 3 generations. And this corresponds to the high case for CO2 emissions and the low case for CO2 emissions, where CO2 emissions in this case, where we reach 90% is sustainable energy, then the CO2 emissions drop from about 31 billion metric tons per year down to about half of that. And in the worst case, CO2 emissions grow by a factor of 4, and you have runaway climate change. So these are, again, this is not the position of the Academy. This is just taken from the literature as it seems to exist. So the way the study was approached, we laid out our goals and objectives, got permission from the Academy to go forward with the study. We established a high-level framework. The study group was chaired by myself and by Professor Nobuyuki Kaya. I'll show you at the end who are the members of the study group. Overall, something like 10 different countries were involved in the study. We formulated global scenarios for energy and the environment, which I'll tell you about. We couldn't make sense of 160 or so different energy scenarios from the Intergovernmental Panel on Climate Change. And then with each of those scenarios with regard to energy growth, there's an alternative mix for what happens with regard to renewable versus non-renewable energy. And then for each of those, there's a different set of projections and models for what does a certain level of CO2 concentration mean in the atmosphere. And I don't know how you make sense of that from a policy standpoint. So what we did is we said we're going to frame global scenarios in the same way that scenario-based analysis has been done previously, like Pierre Wack, or the scenario-based analyses that were done for Shell Oil back in the early 1970s, late 1960s, that kind of thing. We identified high-level figures of merit. We did a formulation of a limits analysis to try to get a handle on what would different levels of performance and cost mean. We identified the high-level trade space, and we invited a group of papers from about 60 or so subject matter experts in space solar power who came and participated in a workshop in Toronto in September of 2009. Now, this workshop was co-organized by the International Academy of Astronautics, working with the kind support of a group called Space Canada, which is a non-profit organization based out of London near Toronto, who should have been here today to introduce this last session, but unfortunately their executive director got tied up in a weather-related travel delay, and hopefully he'll make it in this evening in time for the gala. And from that, then during the last year, the report has been formulated. There have been updates of the limits analysis, trying to identify key performance parameters and so on. There have been some focus studies looking at specific issues, some of which came out of early comments and feedback on the study. And what has been produced in the report is an integrated document of about 300 pages in length that looks at specific systems concepts, which I'll tell you a little bit about more in a moment. It does a technology readiness and risk assessment on those concepts and the key technologies. It looks in brief at the key supporting systems, things like Earth-to-orbit transportation and so on. It identifies and looks at some SPS demonstration options and technologies, and puts together the roadmap which was promised, which I'll show you in a moment. It also looks at a number of key policy considerations and does an integrated assessment on several competing SPS systems concepts based on all of these considerations. Next, please. We identified 3 reference missions to have engineers like reference missions, things that they can chew on. The first was the full-up first solar power satellite, not the 100th or not the 1000th, but the very first one. The goal was an operational SPS delivering baseload power to terrestrial markets at approximately 1,000 megawatts power delivered at a price point of between 10 and 50 cents a kilowatt hour for the first SPS, and then a number of detailed aspects of the reference mission. And then there were 2 pathway missions First, a small-scale demo in the 10 to 100 kilowatt class, and secondly, a pilot plant capable of delivering approximately 10 megawatts into terrestrial markets. And so these were the sort of the points of departure in terms of examining different SPS options. And we did apples to apples across system concepts and technology options. Next, please. We developed a generic functional architecture which pretty much all SPS system concept types must follow. It's not strictly true because there are some variations, but in principle, all of them have some way to take in solar energy, some kind of solar power generation system, some kind of food chain leading to wireless power transmission, some kind of receiver on the ground. Up in space, there's a supporting structure, there's attitude control, there's some kind of assembly system, there's some kind of onboard propulsion, and so on. There's some kind of thermal management for whatever it is, and there are a set of key systems like Earth orbit transportation, in-space transportation, in-space supporting infrastructures, and so on. And then we mapped all of the system concepts that we looked at and all of the particular technologies that go with those system concepts into this work breakdown structure so that we could have a fully integrated technology readiness and risk assessment across the system options. Next, please. It's impossible. There are something like 30 or 40 or 50 or 100 different space solar power system concepts. And it's impossible to really get your hands around that, especially in an effort like this, which was a volunteer effort. What we did was to choose 3. The 3 that we chose were an updated technology version of the 1979 reference system, a modular laser-based approach using diode lasers, and a version of the sandwich concept in which you have the microwave beam and you have the solar power generation and the RF generation in close proximity. Between these 3, they explored microwave and laser. They explored minimal modularity, moderate modularity, extreme modularity. We looked at, as I said, microwaves and lasers. We looked at in-space infrastructures versus self-assembling systems, and so on. There were some other concepts that have been around. We talk about those briefly, but mostly from the standpoint of saying, here are these other concepts, and here are some of the reasons that we didn't choose one of these to be one of the 3. So for example, there's a very nice idea which Jeff Landis came up with some years ago to put a huge solar power satellite at a sun-Earth libration point 1.5 million or 1.25 million kilometers away. There's the concept which has been mentioned in the past couple of days of Solaris. It's putting up a 300-meter diameter mirror, a perfectly flat mirror, and reflecting sunlight down to the surface of the Earth. There's the idea of an extremely long fiber laser concept. There's LEO concepts like the Sun Tower or the Sail Tower. There's the integrated symmetrical concentrator, which came out of the NASA studies of about 10 years ago. And there's lunar solar power that was invented by David Criswell of the University of Houston as an alternative to geo-based solar or Earth orbiting-based solar power back about 20 years ago, or 30 years ago at this point. And I won't go through all the reasons why we didn't choose those, but essentially it was our consensus within the study group that the 3 that we chose, they're all in LEO, they're all in GEO, they all got mapped into the reference missions, they all had to satisfy the same markets, and we analyzed the technologies in terms of the same set of functional breakdown areas. We put together a set of key figures of merit, things like the cost of power, cost like dollars per watt to install, cost of the energy, dollars per kilowatt hour to deliver, and backing from that the size of the modules, the number of modules, efficiencies, and so on. What we did not do, and then based on this we did parametric analyses of key issues. What we did not do is develop an International Academy of Astronautics reference mission system concept. We never did any kind of end-to-end design. This was high level. We didn't want to get into any ITAR issues. So at no point did we say, okay, here's a particular set of technologies and here are a particular set of technology choices and work through those rigorously. We kept it at the systems analysis level. Next, please. Just to show you a couple of specific examples, and you've seen some of these today already. Obviously, one of the key ones is spectrum, and you're quite familiar with the two windows in the atmosphere in terms of electromagnetic wavelengths and when they can get through and when they can't. And that in the RF, in the microwave, that you have the 2.45 and the 5.8 gigahertz, which are ISM, industrial, scientific, and medical bands, which are quite attractive because they're not being used for telecommunications, except illicitly, as we talked about earlier. Next, please. And then from those two windows, then of course there comes the straightforward relationship between the size of the transmitter, the size of the receiver, the distance between them, and the wavelength, in terms of how do you get essentially diffraction-limited optics and beam coupling from the transmitter to the receiver. And so from this, we looked at things like the sizing and the energy density of the beam at the ground for certain sizes of the transmitter and frequency choices and so on. And we basically ended up with 2.45 in the gigahertz in the RF, and about 1 micron in the visible, in the laser case. Next, please. Another issue which comes up a lot, and this is a new result from the study, is Earth-to-orbit transportation. And there's this experience from the 1970s reference system studies that suggests that, and this is in large measure due to the requirement for extremely large in-space infrastructures, as well as some of the key system components, that you must have a new reusable heavy lift launch vehicle before you can build anything having to do with solar power satellites. And in fact, our findings were quite different. What we found was for the size of the pieces that appeared to be relevant, and in particular, in the case of the pilot plant, where we sized a pilot plant, i.e. one that would deliver about 10 megawatts, as being somewhere between 1 and 2 times the size of the space station. So somewhere between 400 and 800 metric tons. That for that plant, in terms of the cost to get that plant deployed, that actually existing ELVs were the best solution. Because you'd be buying something like 40 to 70 of those ELVs, and our estimation was that with a reasonable buy, i.e. you commit to either Delta IV Heavy, or you commit to SpaceX or whoever it is, you're going to buy 40 launches, you can get prices of a few $1,000s per kilogram. One of the reasons why space launchers cost so much is that most of the launchers in use in the world only fly about once a year. But you have to maintain the entire marching army and sustaining engineering and production capacity. You just don't fly very often. So for the initial pilot plant, there's absolutely no need for any kind of new RLV, because it's too much money for what you need. And in fact, existing ELVs would be fine. Now, if somebody else developed a new RLV and it was being shared with other markets, that would be fine. But there's no barrier to doing a space station-sized SPS demo in the Earth-to-orbit transportation system. For the longer term, when you get to the point of saying multiple SPS being launched overall, what you find is you must have a reusable launch system. That you really can't get away with an expendable system and get anywhere near baseload power markets. And that even any kind of expendable vehicle, either a smaller one or a mid-sized or a heavy lift, none of them can come close to the price point. And it's actually somewhat counterintuitive. With the super heavy lifts, you end up making a lot fewer of them. If you're making a lot fewer of them, you don't get the economies of production that you do by making lots of smaller objects. And so they don't actually get cheaper as fast as the things that you're launching. So the launch cost never gets appreciably better. Another issue which came up in questioning and was discussed at some length is how long does it take to pay back the energy that it takes to put this stuff in space, taking all other things as being equal. And so this is an example of one of the limits analysis. It basically just looks at it takes the geo infrastructure as a percentage of the mass of the satellite, where this is 100%. So if the geo infrastructure that you have to put into place to build SPS is of the same mass as the SPS that it's going to build, in that case, the energy that it takes, the time that it takes, the days, not weeks or months, to pay back that much energy is about 26 days. So in terms of the lifetime of an SPS, in terms of the potential value of space solar power in the terrestrial energy marketplace, the energy cost isn't the same as the hardware cost. The energy cost of the SPS and the infrastructure that supports it is trivial. You pay off the energy in days, not weeks or months. It's a fair number of days. It's 3 weeks. And if it's a small fraction, then you're talking less than 2 weeks. So getting it into geo is not, from the standpoint of the energy, is not the issue. Next, please. There are several other different pointing studies that I'll make reference to, but just to alert you that they're there, and you'll want to look for them when you get a copy of the report. One of them has to do with the fuel efficiency of the LEO to GEO transportation system that you'd use. And it appears, quite compelling that you have to use some kind of high efficiency system, like a solar electric OTV or a tether-based system. That any kind of chemical-based system, you end up paying so much to launch the fuel that you use to use the vehicle to get from LEO to GEO that it eats your economics alive. So you need some way to do better than that. There's another one which goes to the issue of energy intensity. And again, this goes to using the Stefan Boltzmann black-body equation, and essentially it's about 5 suns, to answer the question that came up earlier. At about 5 suns on a warm summer day, you ignite wood, paper, asphalt. So if you have anything greater than that, and this is just from a single satellite, you ignite things. Cities, forests, people. And our consensus in the international community, and you'll see that later, is that weaponization was a very big deal. And that the ease of weaponization was a very big deal. Turning now to the technology assessment. So what we did was to look for system concept specific technology requirements across the 3 concepts, which we called the microwave classic, the microwave sandwich, and the laser. And we also looked at generic platform technologies, things like lightweight structures, in-space robotics, and so on. And we looked at supporting infrastructure, things like the launch vehicle and so on. For each of these, we went through and identified a range of particular technology areas like photovoltaic power generation. And within each of those, we identified a range of prospective sub-areas, alternative technology implementations that might be used for that technology function. And for each of the 3 system types, including a bag of the others that I've talked about, we did a technology assessment, including the technology readiness levels, the degree of difficulty of maturing the technology involved, and how critical was that particular technology to one or the other of the SPS system types. And then we went through and we did that methodically. So there's a whole bunch of tables in the report. Next, please. From that, we then synthesized for each of the 3 system types an integrated technology readiness, risk and readiness assessment matrix. And so for the SPS type 1, we found that there's a cluster of technologies. And so basically analyzing the cluster of technologies which are both very difficult, i.e. the R&D cube, the degree of difficulty is high, and the consequences are really severe. And these tend to center for the reference system concept around the power management and distribution. You have this enormous bus bar, you have the solar arrays at one end, you've got the transmitter on the other end, you've got to get a stupendous number of amps from one end to the other, and this power management and distribution system is just extraordinarily hard. It's got a bunch of hard things associated with it. In the case of the modular laser, you end up with a cluster of technologies which frankly look easier, but not trivial. And so this cluster starts to move down. Oh, the only thing which was easy here was that the launch concept was fairly straightforward. It's just a huge space shuttle. And for the sandwich type, the cluster of technologies really appears very, very promising. They're relatively low voltage. The individual modules are not very large. It's basically 10,000 Iridium class satellite buses. But there's one significant problem, which is thermal management. You've got this bunch of small satellites all working in close proximity. You have to do something about the waste heat. And then there's supporting other technology assessment results for the other parts of the system element. It's a system architecture, please. Turning now to the scenarios. So we looked at 4 scenarios. We didn't look at 160 times 2 times 20. Scenario alpha is that everything we're doing now, it turns out it's all going to be fine. Greenhouse gas emissions aren't great, but the steps that we've already got underway are going to take care of it all. There's no need for fusion. There's no need for radical new technology options. As we go forward, we get economic growth. All the assumptions, all of the cases assume that the forecast that I showed a few minutes ago is all true. But no dramatic change is going to happen, is either necessary or is going to happen. Scenario beta says that we proceed as though business as usual was going to work out, but it turns out that greenhouse gas emissions actually do matter, and climate change is occurring on the high end of all the forecasts, not the low end, and by the end of the century we're cooked. I don't know if you know the story. There's a story, I grew up in a farming community, which is if you want to make frog soup, you don't put the frog into the pan of hot water because he'll jump out. You put the frog into a pan of cold water and you heat it slowly. Frog never realizes that he's becoming soup. So scenario beta is we're the frog, and by the end of the century we're in the soup. Scenario gamma looks at the whole issue of resource depletion and the idea that global production of key resources peaks and begins to decline. We came up with this in 2009, and in fact it was just last December, after we had already put this into bed and already submitted it for peer review, that the Energy Information Agency announced that peak global production of oil had been reached several years ago. In our document, what you'll see is we are ultra conservative. We assumed in the everything works out case, in fact, even in the fossil fuel runs out case, we assume that peak oil is still 5 or 10 years away. So even in the worst case that we looked at, we assume that it's not as bad as it actually is, which is peak oil has already been reached. And scenario delta is that more aggressive green policies are pursued and that these basically work. So we had 2 cases where things work out for the best. We had 2 cases where things go to hell in a handcart, and they're fairly diverse in terms of why. And what we did then was to map space solar power for the 3 types of missions into these different scenarios to see how would they work and how would space solar power play in these alternative futures. We put all of these things together into an integrated assessment of the 3 system options. So for example, the RF Classic, our technical criteria included our best estimate of cost to first power for the operational system, the operational SPS, life cycle cost and economic prospects, how low did it appear that the cost per kilowatt hour was going to get, technology readiness and risk based on the assessment that I showed you a moment ago, expected ease of technology maturation, looking at the research and development degree of difficulty in particular, policy issues in terms of, in large measure, focusing on things like spectrum allocation or weaponization, and what was our judgment on how severe these things were going to be, how readily were they going to need to be solved, and prospects for non-SPS applications, a variety of the benefits of those. And what we ended up with is that the RF Classic comes out still very difficult. It does not do well against our criteria, even with updated technologies, because of the significant infrastructure requirements and technical challenges and so on. The RF Sandwich came out the best. Basically, if you build one object of about 100 to 200 kilograms and you can solve the thermal problems, everything proceeds from there. It's very elegant. It's nicely scalable. And the modular laser was about in the middle. Its biggest difficulties were the policy issues. I.e., that the consensus was that a gigawatt laser, any way you slice it, is a city burner. And being unclear how we would feel if somebody put one next to our cities And what would we do about it? Next, please. In terms of the scenarios, so the 4 scenarios, business as usual works out. Everything is fine. RF Classic never seems to really get there. Things are sufficiently rosy that the RF Classic requires this big barrier of new infrastructure to be overcome before you can proceed. If things start to go into hell in a handcart, even the RF Classic starts to look pretty good. Because society is so desperate, you don't mind spending $100 billion in infrastructure before you start building solar power satellites. And if green policies work out, then the RF Classic, again, doesn't look very attractive. The modular electric laser and the RF sandwich, both are almost identical, just neck and neck, in terms of these criteria. And so here's the integrated assessment. In terms of the yellow is the technical and the green is the scenarios, the global scenarios. The overall assessment on the microwave classic, it puts it at the bottom of the heap. There are only certain circumstances when it appears to, like it could possibly be viable. The modular sandwich looks the most attractive. It works under the most, has the lowest buy-in cost and the greatest degree of flexibility in terms of evolution. And the modular laser is good, technically, but has severe policy problems. We did not choose one of those. So it was not part of our charter to recommend the technical answer to the international community. What we did was to put together or to say spend this much money or that much money, but what we did was to put together this roadmap. And this includes another one of the new results from this assessment, which starts with advanced studies and technology research, progresses in a very natural way through system developments for the SPS system, including technology demos and component research, and leading in due course to the pilot plant. So this is the key thing for us, is to have a multi-megawatt pilot plant. And what we discovered, surprisingly, is that there was a strong consensus among the members of the committee that this pilot plant could be realized within 10 to 15 years. That this was not 30 or 40 years away, it was not trillions of dollars, it was billions of dollars, and it was about 10 years. And that was really all that seemed to be necessary. That wouldn't be the system that would deliver 10 cents a kilowatt hour. That would be a system that could be capable of delivering megawatts of power at dollars a kilowatt hour into niche markets, premium markets. The other thing that was very interesting, other than the 10 to 15 years, was confirmation that a critical requirement is to pursue the in-space supporting infrastructure at the same time that the solar power satellite is being developed. As we found, you don't have to have the Earth-to-orbit transportation system to do the pilot plant. It's not cost effective. But you absolutely do have to have the in-space infrastructure, in-space transportation from LEO to GEO, in-space assembly via robotics and so on, in order to do the pilot plant. And then ultimately leading to the beginnings of deployment and operation of the SPS system. There's a set of findings. This is just a summary level findings and recommendations from the Academy to the international community. This is highlighted in draft. I know there are a couple of folks taking pictures and so on. Let me urge you, and look at the camera, let me urge you, and you, don't take this as gospel. This is being reviewed by the Board of Regents right now. I'm told they have comments. And at some point in the next few weeks, I'm hoping to get them, and there'll be updates to all of this before it becomes an Academy-endorsed product. So
those changes will be on the one that we get?
The one that will ultimately go up. I've asked that this one not be put online, but the one that will go online ultimately from this meeting will have the real ones. We'll have the stuff that's finalized.
Thank you, John.
So, finding of the Academy, new energy technologies are necessary. There does not appear to be any way to get from here to there with existing energy technology solutions to get from 10% of 120,000 gigawatt hours per year to 90% of 480,000 gigawatt hours per year
in the next 90 years. You just can't, the IPCC came out with this silly report saying that 60% or 70% of all energy by 2050 could come from sustainable sources, but they assumed there would be a 20% drop in total global energy consumption over the next 4 decades.
They're planning on a war, obviously.
They're obviously planning, or really horrendous disease vectors or something. But if you've got ongoing peace or reasonable peace and ongoing economic growth, it's not going to be true. And it appears to us that solar energy from space could make a significant contribution to meeting that challenge. We agreed with the earlier findings of different groups that space solar power is technically feasible. There don't appear to be any requirements for magic in order to make it viable. And that operational solar power satellites could be achieved within the next couple of decades, with a demonstration pilot plant within the next 10 to 15 years. Absolutely essential that in-depth end-to-end analyses be done with supporting technology developments. Low-cost ETO is enabling for the commercial baseload option, although it's not required for the pilot plant. Next, please. Studies are not enough. We need technology flight experiments and demonstrations. The architectural approaches which deliver power more or less seamlessly into the grid appear to be more likely to succeed than those that don't. So the extraordinarily large SPS, where large is like 5 or 10,000 megawatts in a single receiver, appear more problematic than ones that are smaller, 500 megawatts or 1,000 megawatts, just because it's easier to introduce that into the power grid. The concept is sufficiently transformational that until there are major in-space system demos like the pilot plant, it's unlikely that the necessary investment would be made in the infrastructures and things like reusable launch vehicles. And there are a bunch of policy-related issues, regulatory issues that have to be resolved. In terms of recommendations, first and foremost, that government and commercially funded space solar power studies and technology development should proceed. Future economic analysis should look at the potential role of non-space related government and international funding agencies for the development of SPS. Not all the money should come from space agencies. The government and commercial organizations should look at doing the SSP and related technology developments in cooperation. Policy steps need to be undertaken in the near term, not the farther term, to make sure that we don't go down dead ends in terms of the technical solutions that are made. We have a tendency to really like performance optimized solutions as aerospace engineers. These are not necessarily the ones that society is willing to accept. And that international organizations such as the Academy should play a constructive role in guiding and in coordinating across different countries and different projects SPS and space solar power technology development system demonstrations. And the sort of the mental model that was constructed is to start out with, not saying we wouldn't end up with something like a ComSat, but it's sort of the mental framework that we put into place was that in the near term there needs to be something like an ILIWIG, an International Lunar Exploration Working Group, or the Mars Exploration Working Group. That framework for coordinating different programs and projects within an international framework and for long-term strategic goals like exploration of Mars, that looked like a very workable model for getting the ball rolling in terms of putting together an international, an ongoing international context. Next, please. So where we are, the study was completed last fall. It's reviewed and approved by, it was done under the auspices of International Academy of Astronautics Commission 3, which is Space Systems and Technology Development. It was reviewed and approved by the members of the commission. It went out to peer review within the Academy, 8 peer reviewers, independent review, not involved with the commission, not involved with the study. All 8 recommended publication. 6 recommended publication with minor changes, 2 recommended publication with no changes. All of the comments and changes that they suggested were addressed. That result was recommended, it was forwarded to the Academy Scientific Activities Committee in March in Paris and was approved and forwarded to the Academy's Board of Regents. They've had it for the last 2 months now, and we're waiting for the feedback to come back from them. Our goal is to complete and to publish the study report by sometime this summer, and it really depends on them coming back, and we'll find out whether or not there's some fundamental objection or problem within the Board of Regents for what has been done. If you'd go to the first chart at the backup, these are the main members of the study group, myself and Professor Kaya as the chair and co-chair. Joe Howell here in Huntsville and Henry Brandhorst over at Auburn were members. A.C. Sharania, Ravadan Gopalswamy from India, retired Air Commodore, Koichi Ijichi-san, and Shuichiro Mihara-san, and of course Sasaki Sensei were members from Japan, Leopold Summerer from the European Space Agency, Didier Vassaux from the French Space Agency, and several others, including Frank Little from Texas A&M. In addition to these core members of the study group, there was also the 50 or 60 folks, the subject matter experts who participated in the workshop in Toronto, who contributed papers and so on, including John Strickland, who walked in a few moments ago, just in time to be recognized. And so that's it.